Hello, everyone. Today we're going to continue to chapter 2, describe a single variable using numerical values. So last class, we talked about describing a single variable using a graph. So we learned to use different kind of graph to describe different kind of variables. For example, we use pie chart and bar chart to describe a categorical variable. And then we use stem plot and histogram to describe a numerical variable. So in this course, we're going to focus more on numerical variable because that's the most common variable that we're dealing with in statistical analysis. Categorical variable, we can't really do much about it. So for numerical variable from the graph, either stem plot or histogram, we can observe 5 main features: the mode, the center, the spread, the shape, and the outliers. You can get these measures for the data set very easily from the graph, but they're very subjective. Basically, we roughly estimated those measures. So it will be a lot nicer that if you can quantify them, so we can compare between groups for the same measure very easily. So for example, if one group had center quantified as 4.1 and the other group is 4.0, so we know 4.1 is a higher center than 4.0. It's very easy to compare. So out of all the common measures, the most common ones are center and the spread. That's basically people use all the time. So that's what we're gonna talk about today, center and the spread of the data. So you're still looking at the diagram here. So please, every time we talk about new concept, refer to the diagram and see where it fits. So that way, after the semester, you can link all the concepts together and you're gonna have a good understanding of, why we're learning statistics and how statistics work, right? So we're gonna look at the page full of symbols again. So make sure you memorize all the symbols, as quick as you can. Very quickly, we're gonna use some of the symbols. For example, we're gonna use quite a few today already. So anytime you see a small n, that represent sample size, number of individuals in the sample, and big N, population size, number of individuals in the population. Sigma, population standard deviation, S, sample standard deviation, mu, population mean, X bar, sample mean. Z, standard normal variable, R, correlation between two numerical variables, B1 and B0, the regression slope and intercept. P-value is a probability we used in hypothesis test. And then alpha is a type 1 error rate. We use p-value and alpha compare to make decisions in hypothesis testing, right? So, these are the symbols we're gonna use for the semester. Right, so today we're gonna learn how do we describe data using numerical values. So learning objective, we're gonna focus on the 2 common features, center and the spread. So there are 2 ways to describe the center. So we can quantify the center in 2 different ways. One is mean, the other is median, right? So mean is just average. So everyone know what average is, right? So everyone, you have 10 numbers, then add them all up and divide by 10. That will be the average of the 10 whatever, right? And the median is a different way to find the center. So rather than taking averages, it look for the middle located number. So one number appear right in the middle, that's median. And the spread, we also have 2 ways to quantify the spread. One is called standard deviation, and the other called interquartile range, IQR. Right? So we're going to talk about how are we going to find, those measures for any given data set. And then there's another concept called the 5-number summary. So we're going to talk about the 5-number summary, how we obtain those 5-number summary from any data set. And from the 5-number summary, we can make another chart, a graph, to describe the data. That's called a box plot. Box plot is very widely used in statistical world as well. And then in commercial softwares, if you get a box plot from a software, a lot of software will provide a box plot with outliers being indicated. So they're being marked out outside of the box. So how are those outliers identified? We learned we can identify outliers from stem plot and histogram, right? But when we identify outliers from stem plot and histogram, it's very subjective. So different person, when they look at the same histogram, they may have different opinions about if a data set if a data values should be an outlier or not. So box plot is different. The outliers indicated by the box plot are being accurately calculated. So we're going to learn about how do we calculate to identify outliers with a rule called 1.5 IQR rule, right? And then lastly, it's a common term called a resistance measure. So we need to understand what the resistance measure is. And then out of all the measures we mentioned earlier, which ones are resistant, which ones are not, like a mean, median, right? Okay. So we're going to start with center. We mentioned earlier, we have two ways to find a center. One is mean, the other is median, right? Mean is taking average. We use a symbol X bar represent. You have a bar on top of X. We call it X bar. And this is just like a taking average function, right? Adding all the values up, divided by number of individuals taking average. So here, we don't like to write the long addition series of all numbers, right? So we can use a simple notation, the sum function, the big sigma, that's a sum function. So sum of xi is just x1 plus add x2 plus x3 and so on, just adding all the numbers up. So I'm going to spend a little time on the sum function because we're going to use it quite a bit. I want to make sure everyone understands what this sum function is. So like I mentioned, the sum function is just adding a bunch of numbers. So if you only have one symbol, xi, worked by the sum function, basically just add all the numbers from I equal to 1 to 2 to 3 up to I equal to n. If you have n individuals in sample, right? Every individual have a value being measured. And then the sum function can also work on an expression, but it's the same deal. It's going to add n of these expressions up by changing I from 1 to 2 to 3 up to n. So sum of xi minus 3 will equal to x1 minus 3. That's the first item. And second item is x2 minus 3, and so on. And the last item is xn minus 3. And then you can also, have a sum of xi minus 3 take a square, right? So the first item is the whole thing as a whole item, changing I equal to 1, right? x1 minus 3 take a square. Then next, should be x2 minus 3, then take a square. And then up to xn minus 3 take a square, right? So the sum function just adding up things, right? So we're clear about the sum function, right? We're gonna see that a lot in a class, so don't get confused. So everyone know how to find mean, right? So now let's talk about median. Median is a midpoint of data values. So if you have a bunch of values for your sample, then you just sort those values from lowest to highest. And then depending on if the sample size is an even number, odd number, you have different ways of finding median. So let's look at an example. So for example, if we add a few, if you just make up of some numbers for a data set. So for example, if you have 2, 3, 6, 8, 10, 12, and 15, right? So we have these 1, 2, 3, 4, 5, 6, 7 numbers. That means we have a sample size n equal to 7, right? And 7 is an odd number. So when we have odd number of observations, we need to find the number right in the middle of the data set as a median. So one way to do it is we can calculate it. So we use n plus 1, then divided by 2. And that's very simple, right? 7 plus 1 divided by 2 equal to 4. So that'll be number 4 in the sorted list. So then if you look at the data set, number 4, 1, 2, 3, 4. So this number appears right in the middle of the data set. That will be our median, right? And if you don't like to do calculation like this, it's okay. You know, what you need to do is just count from both sides. You know, 1 here, 1 here, right? Yeah, 2 here, 2 here, right? And when you count by the end, so you can see there's a number right in the middle, right? That's your median, okay? Right. So this is when n equal to 7, when you have even number observations. What if we add another number? So for example, if we add another number 18 in the data set. So now if you look at this, n equal to 8 now, right? So 8 is an even number, right? So for even number, there's not just a one single number in the middle. If you count it, it will actually have 2 numbers in the middle. So we can calculate these 2 numbers location more quickly by n divided by 2. That's 8 divided by 2 will equal to 4. And then n divided by 2 plus 1. That will be 4 plus 1 equal to 5, right? So the middle 2 number will be number 5, number 4, and number 5 in the list. So 1, 2, 3, 4, 5, right? So it will be between these 2 numbers. Sorry. Number 4 and number 5, right? 1, 2, 3, 4, 5 between these 2 numbers. So you can count on both sides as well if you don't like to calculate. So 1 and 2 and 3. And then you can see you have 2 numbers in the middle, right? So the median is a number in the middle, but we don't want to use 2 numbers. We want to simplify it. So the best way to do it is we're going to just take an average of the middle 2 number. So the median will equal to 8 plus 10 divided by 2. We're taking average of them, right? And that will equal to 9, right? So median is 9, and here median is 8. So this is how we find the median. It's pretty straightforward. It depends on if n is odd or even. If n is odd, there will be 1 number in the middle as itself. It's median. If n is even, you can have 2 numbers in the middle, take an average of the middle 2 number, that's your median, right? Okay, so we know how to find the mean and median now. Let me erase this. It's kind of confusing. We highlighted over earlier, right? So now let's look at a small data set, for example. So we have a small data set, 9 numbers. This shows 9 workers' travel time from home to work in North Carolina. So we have 5 minutes, 10 minutes, 10 minutes, 12 minutes, 13, 20, 25, 28, and 31. So then we need to find the mean and the median of the travel time and make a stem plot also. So stem plot we learned from last class, right? So look at the stem range from 0 to 3, and then put a corresponding leaf on the stem so we can look at, the mode, the center, the spread, the shape, and the outliers very quickly from the stem plot. So we're only going to focus on one thing here. Do we have outliers from the data set? Apparently, all the data values together, right? So there's no outliers. And then we can find the mean by taking average. We can then find a median, by finding a middle located number, right? Mean is 17.1 and median is 13. So now we want to make a little change. So if we change the 31 into 51, then when you make a stem plot, and when you look at the outlier, it looks like this number 51 is outlier, right? This is outlier. So then for this new data set, if we calculate the mean and the standard deviation, mean will be 19.3 and the median will be 13. So here we're going to introduce a concept called the resistance measure. So what does resistance measure mean? It means the measure is resistant to the outlier effect. So if you introducing outlier is not going to affect that measure, we call that measure a resistant measure. Otherwise, it's not resistant. So then when you look at the mean and median, which one is resistant to the outlier effect? So it's clear when you introduce outlier here, median is not affected. Median is 13, right? Before and after you introduce outlier, but the mean got affected, right? So mean is not resistant and median is resistant. That's what the resistant measure means. If the outlier is affecting the measure, that's not resistant. If the outlier doesn't affect the measure, that measure is resistant. So imagine if you change the 31 into like a million, right? You can see the mean will change a ton, but median will stay the same, right? So we learned about that we need to pay attention to outliers for any statistical analysis. Why is that? Because most of the time when we do a statistical analysis, we use mean instead of median. And mean will be affected by a lot by the outlier. That's why we need to pay attention to the outliers. If you were to do analysis using median instead of mean, then you don't have to pay attention to outliers anymore because outlier doesn't affect median, right? Okay. So now we learned center. So we mentioned earlier we're gonna always describe center and the spread at the same time. So why do we need to pay attention to spread? Why can't we just describe the center and call it done? Most of the time we just compare the center anyway. So for example, when you're comparing class averages on the exam score, we just say, hey, the average of this class is 78 points and average of the other class 76 points, and this class is higher than that, right? So why do we just stop after we find the center? Right. So let's use a small example to kind of explain this. Hope that makes sense. So if a researcher is comparing the lifetime of two types of car batteries, the two samples randomly selected for each battery type. We have 7 batteries tested for each types. And their data are given below. These are made up data, but just for illustration purpose. For the type A battery, the lifetime of the 7 batteries are 1, 2, 3, 3, 3, 4, and 5. For type B battery is 2.8, 2.9, 3.0, 3.0, 3.0, 3.1, 3.2, right? So which battery would you buy and why? So If we want to look at the center, either by mean or by median, for type A battery and type B battery, what's the mean for type A battery? You calculate average, right? If you calculate it, you can see it's 3.0 years. For type B battery, it's 3.0 years as well, right? So it has exactly the same mean. Then someone may say, hey, I don't like using mean because mean is not resistant. I want to use median. So then for type A battery, the median is 3 years. And for type B battery, the median is 3 years as well. So it doesn't matter what measure you look at, mean or median, the two type of batteries are giving you exactly the same center. Does it mean the two type of batteries are the same? Clearly not, right? So there's something different between the two type of batteries are not being described. And someone already see what it is, right? The spread of type B batteries from 2.8 to 3.2. The spread of type A batteries between 1.0 and 5.0, right? So we can see their spread is being different. So if you want to describe the data in full, we have to describe center and spread. So now we're going to talk about how do I describe spread. So this is the first animal for attendance check. It's an owl. And now we're going to talk about measuring spread. So there are two ways to measure center. The same here, we have two ways to measure spread. The first is called the standard deviation. And the standard deviation always come together with variances, all right? So there's a simple relationship between standard deviation and variance. Standard deviation is S and the variance is S squared. So for example, if the standard deviation of data is 4, then variance will be 16 and vice versa, right? If the variance is 16, then standard deviation is square root of 16 will be 4. Something need to be careful with. Standard deviation has to be positive or at least 0. It cannot be negative. And then standard deviation is not resistant, so it will be affected by outliers, right? So now we know what the standard deviation is, and we have an equation to calculate it, right? So then how do we calculate standard deviation using this equation? So we're going to spend a little time to explore this formula. So the square root function is very, very common function. Everyone know what it is. And then the fraction function, just like a dividing, right? So n, that's sample size, right? Remember, it's n. Anytime you see a little n, that represents sample size. And then x bar, that's sample mean, right? So we already know how to calculate sample mean. So sample mean is going to be a constant number here. And then you have this summation function. The sum function, just adding a bunch of these squares, right? And that's it. Okay, so we're going to talk about how do we calculate standard deviation using a small example. So for example, if you have a small data set with 5 numbers, and the values are 1, 2, 3, 4, and 5, right? So sample size n equal to 5. 5 values. So if you want to calculate standard deviation, you notice the standard deviation formula is right here, right? So the square root function is simple, and then the fraction is simple. We need to pay attention to this sum of xi minus x bar squared. So if we know how to calculate it, if we know what this is, we just need to plug into the equation, right? And that the problem solved. And earlier I mentioned, we talked about the sum function, right? when you have a sum function work on an expression, it will be just adding n of these expressions up by changing the index I from 1 to 2 to 3 up to n. Again, should be 2 instead, and so on, right? So we have a very similar format. Instead of 3, we have x bar here, right? So we just need to find out what x bar is. Then it will be the same expression, right? And x bar is sample mean, right? So if we can calculate this sample mean, then we can just replace that x bar in that sum function. And basically, we'll add up all the numbers, 1 plus 2 plus 3 plus 4 plus 5, that's sum of xi, right? So on top, it will be, if you add it up, it will be 15. And what is n? N is sample size, right? So we have 5 individuals in sample. So this is actually equal to 3, right? So then this will, xi will be each of the values. For example, x1 equal to 1, right? And x2 equal to 2, right? And so on. x3 equal to 3, x4 equal to 4, x5 equal to 5, right? So then we just plug in numbers. This will be equal to a bunch of these numbers add up together. So we know there are 5 of them. I'm going to make a little change, copy and paste here. So this will be x3 minus 3, and this will be x4 minus 3, right? And x5 minus 3, n equal to 5. Once you get 5, it ends, right? So then we can calculate very quickly. So we can plug in numbers. So we know x1 equal to 1. So my Excel is, my Word is not responding very well. And x2 equal to 2. x3 equal to 3. You know, just plug in numbers, right? And x4 equal to, this should be x4. I didn't change it. x4 equal to 4. x5 equal to 5. Right? Then we calculate, right? These are simple algebra. So 1 minus 3, that's negative 2. Then take a square. And then 2 minus 3, that's negative 1. And then take a square. And then 3 minus 3 is 0. And take a square. And 4 minus 3 is 1. Take a square. And 5 minus 3 is 2. And take a square, right? So if you calculate it, that'd be 4 plus 1 plus 0 plus 1 plus 4, that equal to 10, right? So once you know this sum of xi minus x bar square, now if you look at the standard deviation calculation, the top summation is just calculated to be 10. And the sample size n will equal to 5. So this will equal to square root of 10 divided by 4, 2.5, right? So then you can use your calculator to calculate. very quickly. So it will be 1.58. Right? So that's the process of calculating standard deviation. Some people may say, hey, this is too lengthy. And I agree. You know, when you have a larger data set, and also when the data set is not as friendly, it will cause some problem. So now we're gonna talk about how do we find the standard deviation in a better way or a systematic way, right? So we're gonna start here. I'm trying to make this displayed better, right? Too much. Huh. Sorry about that. Just a little bit up, not too much. All right. So it will be the same amount of calculation, but this is very, very systematic. And it's, in my opinion, is way better than going through those lengthy, you know, expressions. And it's very easy to make a mistake here because it's too long. So here is what you need to design as a worksheet. Xi, X bar, the sample mean, right? And xi minus x bar, xi minus x bar square. So we're going to start with xi column. Xi will be the values of your data set. It's a raw data. So for example, in this case, we have 1, 2, 3, 4, and 5, right? And then on the bottom, we have a total column. So total is just adding the whole column up. So 1 plus 2 plus 3 plus 4 plus 5 is 15, right? So here is important. So once you realize the column total, then you need to understand the column total is just like a sum function. Adding all the xi's up, that's just sum of xi, right? So you should realize sum of xi equal to 15. Then from here, we're going to borrow the formula to calculate x bar. So then it's very simple, right? The sum of xi equal to 15. So everything on top of the fraction is 15, that n equal to 5. So then sample mean is 3, right? That's x bar. So x bar equal to 3, then that will be the second column. We need to fill it all the way up to 3, but you know, ignore the column total. You don't need the last two, the column total here. But if you want it, it'll be 15 as well, right? But we're not interested in this. You don't have to calculate this, right? So the next column is xi minus x bar. So you're going to use your xi column, subtracting x bar column. So 1 minus 3, that's negative 2. 2 minus 3, negative 1. 3 minus 3 is 0. 4 minus 3 is 1. 5 minus 2, 5 minus 3 is 2. Right? So that's it. So you don't have to calculate this total, but if you do, it's 0, right? But we're not interested in this column total either, okay? And then the last column is xi minus x bar squared. So you basically have xi minus x bar here already. All we need to do is take a square of this column, right? So whatever number in this column, take a square of it. And here you need to pay attention. Anything square will be a positive number, right? So pay attention to the negative numbers in this column. They all need to be converted to positive when you take a square. So 4, 1, 0, 1, and 4. Okay, so here on this column, we can calculate the column total. So 4 plus 1 plus 0 plus 1 plus 4 equal to 10. Okay, so here, just like how we realized the 15 is sum of xi, I hope you can realize 10 is sum of xi minus x bar squared, right? This is adding all the xi minus x bar squared from x1, x2, x3, x4, x5, right? So then we should realize the sum of xi minus x bar squared will equal to 10. Then from here, we can borrow the formula sample standard deviation will equal to, we know the top summation now become a number we know, 10, right? And the bottom is 5 minus 1. So again, if you calculate using a calculator, it's 1.58. So this is how you calculate the sample standard deviation. Right? Any questions? Okay. So then for any given data set, you should be able to follow the process to calculate the standard deviation. I really recommend you to use a worksheet, and this is how we test your skills also. So on the exam, I don't want you to waste too much time to generate the worksheet, so I will give you an almost complete one. You're gonna see an example on the homework, except that I'm gonna blank out some shells, but it should be very easy to figure out those numbers and then use the algorithm to find the mean and standard deviation. And any statistic calculation can be done very similarly using the worksheet. So like we're gonna talk about correlation and regression. It can be done very quickly through the worksheet method as well, right? So then we calculate a standard deviation 1, 2, 3, 4, 5, right? So then can we calculate standard deviation of 11, 12, 13, 14, 15? Right, so let's take a look. So I'm gonna copy everything here. And since we're not gonna use this anymore, I'm gonna paste it over here. Something is not right. I just wanted to see the, the comparisons between the two group of numbers. Right. So if we start the data with 11, 12, 13, 14, 15, right? So then the column total on the xi column will become 65. And if this is 65, you should realize the sample mean x bar will be 13, right? So then x bar column will be 13 all the way instead of 3. So then after that, you can realize, hey, everything else is duplicates, right? So the standard deviation of these 5 numbers, 11, 12, 13, 14, and 15, are the same as the standard deviation of 1, 2, 3, 4, and 5. So does it make sense then? Keep in mind what the standard deviation measure. Standard deviation is a measure of spread, right? So when you have exactly the same spread pattern, then they should have the same standard deviation, right? So then we can realize, standard deviation of any 5 consecutive integers are gonna be the same, right? So their standard deviation of 101, 102, 103, 104, and 105 is 1.58, right? 85 consecutive numbers has the same spread. They should have the same standard deviation. So in the homework, there's another kind of question that we'll ask. So for example, I can ask you, what's the compare two set of data for mean and standard deviations. So for example, I have 1, 3, 7, 9, and then I have 2, maybe 11, 13, 17, 19, right? So this is group B, and this is group A. So I can ask you, which group has larger mean, which group has a larger standard deviation, but don't calculate it, just look at the data. So obviously, B has a larger mean, right? Because every number is bigger. What about standard deviation? When you look at it, it has exactly the same spread pattern, right? So difference by 2, by 4, by 2, by 2, by 4, by 2, right? So they should have the same standard deviation. So now, what if I change this 19 into 18? Apparently B has a larger mean again, right? But standard deviation wise, which one has larger standard deviation? It's clearly A, right? If it is 19, it has the same spread, but when you change to 18, the spread become smaller, right? So you have a smaller standard deviation. Okay, so sometimes we can, roughly estimate the standard deviation, but just look at the spread of the data. Right, so that's how I find the standard deviation, and that's a measure of the spread. So now we have another measure of the spread. It's called interquartile range, IQR. So how do I find interquartile range? Interquartile range is calculated by the difference of two quartiles, Q1 and Q3. So now I need to learn a new term. What's a quartile, right? Okay. So think about if you have a data set. A data set is like a long rod, right? If you, sort the data into, from smallest to largest. So quartile is basically a point to cut data into quarters. If you want to cut the data into quarters, how many cuts do we need? We're going to need 3 cuts, right? I mean, these are endpoints, they're not cuts, but the 3 points in the middle are the 3 cuts we need to cut first quarter, second quarter, third quarter, and the fourth quarter. So those 3 points, the point in the middle, we already learned what it is, right? This is called a median. Then what about the first cut here? We call that a first quartile, Q1. Right? And then similarly, Q3, third quartile, will be the next cut. Right? So then for a data set, if you find overall median, then we can find quartiles very easily. Basically, we just need to use the overall median to separate data into 2 halves. Then for each half of the data, we find a median again, right? So the median of the first half of the data is Q1. The median of the second half of the data is Q3. So then here is something very important. So don't get confused. When we use median to cut the data into 2 halves, here's the rule. All the values to the left of your overall median is your first half. All the values to the right of the overall median is your second half. So median is not included in either side. All right? Okay. So for example, let's work on a few numbers to find the overall median. So for example, we're going to add a few numbers, 1, 3, 7, 9, 11, 15, 19, 21, and 27, right? We're gonna delete all these and oh, I couldn't delete it. Never mind. All right. I should have just opened a new page, but anyway, we're done. All right. So how do I find quartiles? First, we need to find overall median. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 numbers. Then overall, this is odd number, right? So we have one number right in the middle, will be number 5. 1, 2, 3, 4, 5. Or you can count from both sides. 1, 2, 3, 4, 5, right? So this is our median. Then we can find the quartile by dividing the data into two halves. To the left of your overall median will be the first half of your data. To the right of your overall median will be the second half of the data, right? So do not include your median on either side. That way, for the first half of data, we can find a median again. So we see median equal to 11, right? Then for the first half data, we have 4 numbers, right? The median will be the middle of 3 and 7, right? So then for the median of the first half is Q1. So that'll be the average of 3 and 7, right? So that'll be 5. And similarly, for the second half of the data, find the median again. That would be between 19 and 21, right? So it will be average of 19 and 21. So the median is, the median of that is 20, that's your Q3, right? So you have Q1, median, and Q3. Then we can find IQR very quickly because IQR equal to Q3 minus Q1, right? That's the formula. So Q3 is 20, Q1 is 5. So we know IQR is 15. So that's how we find IQR. Okay. Right, so here I want to talk a little bit more about this. So what if we have a data set that has another number added? So for example, we add another number 30, right? So we need to find the quartiles, IQR. So now we have 1, 2, 3, 4, 5, 6, 7, 6, 7, 8, 9, 10. We have 10 numbers and they call it even. So in this case, the median will be the average of the middle 2 number, right? Will be number 5 and number 6 taking average, right? So median will equal to 11 and 15 take average. So that will be 13. So median location-wise, it's right here, right? It's not 11, it's not 15, but it's a number in the middle. So then the first half will be all the values to the left of the median, including 11. Or the number to the right of the median will include 15, right? So now if you look at the median of each half, we can see very quickly, we have 5 number on the first half the median will be 7. It's in the middle, right? And then the second half, median will be 21, right? So you can calculate IQR by the difference of those two. But the key thing is, depending on even odd number of observations, for odd number of observations, median is not counting on either side. Say missing a value when you divide it in halves. When you have even, then no value is missing, right? Because median is not the real data values in the data. It's a fake value, right? Okay. So now let's go back. All right. So we know how to find quartiles and IQR. So now we have a new concept called 5-number summary. So basically, just think about your rod business. So you can find Q1, median, and Q3 from the data, right? If you include the minimum and the maximum value, that will give you 5 numbers about any given data set. And these 5 numbers are called 5-number summary. 5-number summary is very important because we can use a 5-number summary to generate a chart called a box plot. So box plot, basically, you're gonna need to mark the 5 points in a given data set, minimum, Q1, median, Q3, and the maximum. Once you have those 5 points labeled, you have a line axis here. So then generate a box between Q1 and Q3. Inside the box where median location, draw a line across. And from bottom of the box, draw down the minimum. From top of the box, draw up to maximum. So that's how you draw a box plot. Box plot is very, very commonly used. Okay. So for example, we're gonna work on a data set. So we have 16 potatoes. They're measured in ounces. So we need to find 5-number summary of the data set and then draw a box plot. So, you can find overall median is 6.3, right? Because that's number 8 and number 9, right? And then to find a quartile, you need to use overall median. Overall median is between 6.3 and 6.3. Position-wise, you need to include all the number to the left as the first half and all the number to the right as second half, right? So find Q1 on the first half, Q3 on the second half, right? So combined with your minimum number 3.7, maximum number 15.0, you have your 5-number summary, right? Okay. Then from the 5-number summary, we can draw a box plot like this. So I'm gonna show you very quick how do we draw a box plot. So let's get the 5-number summary copied, and then we're gonna draw it in here. So then to draw a box plot, we need to make axes. Okay, so this is the variable you're describing. For example, we are describing potato weight, right? So this is weight of potatoes. So then this is a numerical axis. So then we need a label. We need to make sure to label it appropriately. So for example, we can label here as 0. And then we can put another mark here as 2, maybe 4, 8, 12, 16, right? So this is 4 on the right. 4, 8, 12, 16. Right? So then we need to find the corresponding mark for the 5-number summary. So for 3.7, it's somewhere here, right? Below 4. And 4.95, it's close to 5, so about a quarter above 4. This is Q1. And 6.3 is median. So 6.3 is kind of a little above the middle of 4 and 8. So, if you have a ruler, it's very easy to label them. And 7.5 is very close to 8. Okay, and then you have a 15.0. 15.0 is close to 16 here. So you have 5 marks. You need to realize from bottom top is minimum, Q1, median, Q3, and maximum. So then between Q1 and Q3, we draw a box. So the widths, this side, the side, X direction, how wide it is, it doesn't really matter. What it matters is on the Y direction here, right? So then across the box where median is, you draw a line. And then on top of the box, you draw up to maximum. This is not a straight line. Sorry about that. And from bottom of the box, it's draw down the minimum. This is ugly box plot, but just for demonstration purpose. Okay, so drawing box plot is pretty easy. Right. So then, right, so this is the second animal for the attendance points. This is a giraffe. Okay. So this is the last concept. How do we identify outliers from the box plot? So we have a rule called 1.5 IQR rule. The rule says if you have any value that falls 1.5 IQR above Q3 or 1.5 IQR below Q1, they're considered as outliers. Right? So it will be very easy to understand if you look at the box plot we just draw. I'm going to try to explain here. So we can see here between Q1 and Q3, this distance is inner quartile range, right? That's IQR. That's the distance between Q1 and Q3. So what is outlier? Outliers are considered as points that's far away from the center. The middle box is your 50% of your data. So that's your middle 50%, right? So if a point that's far away from either side of your center, they're outliers. The question is, how far away, right? So here's the deal. We're going to use IQR as a gauge to measure, but IQR is not long enough. We're going to make it 50% longer. So we're going to multiply this by 1.5. So that's called 1.5 IQR, right? So then we're going to use this distance as a measure. We're going to go from Q3 up 1.5 IQR. We're going to go from Q1, go down, same distance. So then this distance is 1.5 IQR. This distance is 1.5 IQR as well. Then through the calculation, if any points that's below or above the 2 thresholds we just calculated, they're considered as outliers. So basically you can calculate the threshold here. You can calculate the threshold here, right? Anything within the 2 threshold are good data. Anything that's beyond, outside, they're outliers. So in the commercial box plot, from the commercial software, the points outside of the whisker is outliers by calculation. All right, so now let's look at an example of calculating outliers. So I'm going to use the example we just did. So we already have 5-number summary here. So you have Q1, 4.95, and Q3, 7.5, right? So just like how it did the box plot demonstration, first we need to calculate IQR. The distance between Q1 and Q3, that's 2.55. So basically, that's your IQR right here, this distance right here, right? And now we need to multiply it by 1.5 to make it a little longer, right? So 1.5 multiplied by IQR will be 3.825, right? Then we need to calculate the upper threshold. We're going to start from this point. This point is Q3, right? The top of the box, and go up 1.5 IQR. When you go up, we need to increase, right? We need to add. So we're going to use Q3 add 1.5 IQR. That would be 11.325. And similarly, from bottom of the box, we draw down to minimum, right? We draw down 1.5 IQR. So when you draw down, you're going to subtract, right? We use Q1 subtract 1.5 IQR. So then that will be, 4.95 subtract 3.825 is 1.125. And here we can go back to the data. Any values in the data set here, right? If they are below 1.125 or above 11.325, they're considered as outliers. And obviously, from the data, we have one outlier, 15, that's above 11.325. Right. So this concludes today's class. Very quickly, we're gonna summarize this. To describe data numerically, we need to find two measures. One is center, the other is spread. They need to be described at the same time. One is not enough, right? Center is the average or middle value. Spread is, how much spread the data values are from each other. Are they close to each other or they are far away from each other? They're both very important. And for center, we have two different measures. One is mean, the other is median. And for spread, we have two measures. One is standard deviation or variance. The other is interquartile range, IQR. So we need to be able to find any of these measures for any given data set. And then we need to realize some of the measures are resistant, some are not. The only resistant measures are the location-wise measures, like median, quartiles, interquartile range. These are resistant measures. They are not affected by outlier. Mean, standard deviation, variances, they are not resistant. They will be affected by outliers. Then once you find the median and quartiles combined with the minimum and the maximum, that will be called a 5-number summary. You should be able to find 5-number summary for any given data set. And then based on that 5-number summary, we can draw a box plot. So the box plot basically give you 3 cuts in the middle, median, Q1, Q3 to cut the whole data set into 4 quarters. So in between each of the number, you have 25% of the individuals in each of the quarters. Okay. And then in box plot, all layers are identified by calculation. So it's by 1.5 IQR rule. So you need to understand what 1.5 IQR rule is and how do we calculate for the thresholds to identify outliers. Right. So this concludes it. And let me know if there's any questions. You can send me emails. Thank you.